All right, this video is on the fundamental theorem of calculus. So I just wanted to walk through that proof and then walk through a couple of examples. So if we have this graph here, y equals f of t, and it's bound by a and b, our fundamental theorem of calculus states that if we take the derivative of this value here, it's equivalent to f of x. So I just want to look at why that's true. So we're going to call this a, we're going to call this x. This is going to be some value past x, so we're just going to call it x plus h. And we don't really need, actually I'm going to go ahead and move this over here. At some point we're going to call that c. Okay, so let's look at this proof. So this capital F of x just represents that we are integrating from a to x the function f of t. So this represents that we're going to take the derivative of that. So we're going to use from first principles to do that. So that's going to give us f of x plus h minus f of x divided by h. And again, this is the limit as h approaches 0. So what is that equal to? Well, first let's think about what is this saying. This is representing that we are integrating or calculating the area under the curve of x plus h. So we are calculating the area from a to x plus h. That's what that means. So we can write that as a to x plus h of f of t dt minus f of x. Well, that's the area from a to x. So minus the area a to x, f of t dt. And that's still divided by h. So let's look at what that's really indicating here. So we are taking this area from a to x plus h, and we are subtracting the area from a to x. So we are subtracting this area from that. So what we are left with is the area under the curve from x to x plus h. So we can write that as x, area under the curve, so we're integrating x to x plus h of f of t, and again, still divided by h, so times 1 over h. So when we look at that, first thing that should come to mind is mean value theorem for integration. So that is equivalent to some value f of c. So remember, mean value theorem just states that if you have this interval, x to x plus h, there's some value in between x and x plus h that represents the average height. So this is representing the average height. So f of c is going to be somewhere about there. So that's equivalent to f of c. So remember, or if we just look at our graph, we can see that c is between x and h. So that inequality is always going to hold true. So if we look at the limit as h approaches 0 of f of c, let's look at what that's equivalent to. So I'm going to go ahead and erase some of this. Ooh, that's not big enough. Okay, so again, we're looking at the limit of f of c as h approaches 0. That just means what's going on with f of c when h gets closer and closer to 0. Well, remember, c is going to be sandwiched in between x and h. So here, as h approaches 0, that means this value gets closer and closer to x, because this is x plus some value of h. So as it gets closer and closer, remember, c stays between. So they're all getting closer and closer. So as x approaches, or as h approaches 0, we're getting closer and closer to x. So as we get closer and closer to x, f of c approaches f of x. So we can say that that's going to be equivalent to f of x. Okay, so that's kind of a semi-informal proof of the fundamental theorem of calculus. Now let's go ahead and work through a couple of problems. So here, let's look at, we have 1 to x of sine t dt. So this satisfies our theorem here. We have a to x, f of t, and that states that if we take the derivative, that's going to be equivalent to f of x. Well, so we take our function. Remember, if we take the derivative of an integral, it typically undoes the integration. So that's going to give us sine as a function of x. And we're done. That's all we need to do for that problem. So let's look at one where it's a little bit more complicated. Let's say this time we're going from 1 to x squared of cosine x. Or, sorry, not cosine x, cosine t. So this one's a little trickier because we are integrating instead of x, which is what our formula provides us with, we are integrating f of x, or sorry, deriving f of x squared. So we're just going to use the chain rule to deal with this. So remember, chain rule, take the integral of the function itself, and then, or sorry, take the derivative of the function itself, and then take the derivative of what's inside your parentheses. So we need to take the derivative of x squared. So that's going to give us cosine, I'm going to plug in x squared for t, cosine x squared times the derivative of x squared, which is 2x. Okay, so let's do a couple more. So let's say we have x squared to 5 et dt. Okay, so there are two problems we have going on here. One, we have an x squared. Two, we have our constant here, and we have our variable here. So let's deal with that first. So that can be rewritten as negative 5 to x squared dt. Now why is that? So let's look at just a regular function here. It doesn't matter what we have. Let's just call that f of x. So when we evaluate that, we're integrating and we're evaluating it from b to a. Well, what happens if we flip those? So now that's going to be equivalent to f of a minus f of b. So all that did is changed our signs here. So if we rearrange this, I'm just going to factor out a negative. That's negative f of b minus f of a. Well, this is positive f of b minus f of a, and this is equivalent to this integral, so we can just pull that negative out. So that's why that's allowed. So now we have it in a more workable format. Man, my eraser just absolutely hates me. Okay, so let's go ahead and evaluate this. So again, we have a formula for f, capital F of x, but we're evaluating f of x squared, deriving that. So we have to use, again, the chain rule and multiply by the derivative of this value here. So by the derivative of x squared. So that gives us negative e to the x squared times the derivative of x squared, which is times 2x. So you should really write that as negative 2x times e to the power of x squared.